All right, welcome back, everyone. Today, we are opening up a strategic playbook for one of the most intimidating, yet absolutely fascinating chapters in all of physics. If you've been prepping for competitive exams, you already know the name. Yep, electrostatics. It's the whole foundation of electromagnetism, and honestly, it can feel like an absolute monster of a topic. But today, we're going to explore it together, demystify the examiner's traps, and uncover the high-level strategies hidden within the source material. So, let's level up our physics game. 10%. Just think about that for a second. Across various shifts of the joint entrance examination, electrostatics accounts for up to 10% of the entire physics paper weightage. That is massive. Conquering this single domain gives you an undeniable edge. We're not just talking about a random chapter here. It's a major, fundamental pillar of your final score. In fact, our source material literally calls mastering this topic the definitive metric for success in the joint entrance examination. You can kind of think of electrostatics as the ultimate boss level. It demands that you start with the basic interactions of discrete stationary charges, and then you have to bridge your way up into complex, continuous fields and energy landscapes. It is the absolute gatekeeper to the rest of current electricity and magnetism. But how you actually tackle this boss level depends entirely on the arena you're in. There's a stark contrast in strategy here. So JEE Mains, that is primarily a test of breadth. It's hyper-focused on direct applications of fundamental laws and formula-driven numericals. You just need to know your formulas cold. But JEE Advanced, man, that is a whole different beast. Advanced papers demand a multidimensional approach. They absolutely love to synthesize electrostatics with classical mechanics, rotational dynamics, and heavy calculus. You aren't just calculating force. Actually, scratch that, you are calculating force, but you're also finding the motion of a particle in a completely 3D field. Okay, let's dive into this. Here is our tactical battle plan for today's explainer. 1. Mastering the core arsenal. 2. Flux, potential, and symmetry. 3. Conductors and capacitors. 4. The mechanics fusion trap. And finally, 5. Winning the JEE endgame. All right, starting off with section 1. Mastering the core arsenal.
So it all starts with the properties of the electric charge itself. There's some very strict theoretical constraints we need to lock down. First step is quantization, where total charge is always an integral multiple of the elementary charge, Q equals N times E. You are going to see this tested all the time in electron transfer problems. Then there's conservation. The net charge of an isolated system is always constant, which is a total lifesaver in problems involving the contact of conducting spheres. Finally, we've got relativistic invariance. Unlike mass, the magnitude of a charge literally doesn't change, no matter how fast it's moving.
Now, Coulomb's law gets pretty complicated when you start dropping charges into different mediums, but what happens if a dielectric slab only partially separates two charges? Now, what's really interesting about this slide is that a lot of students will try to set up these incredibly tedious calculus integrations here, but top performers, they use the concept of effective distance. You take the original distance minus the slab thickness and add the thickness multiplied by the square root of the dielectric constant K. Plug that resulting effective distance right into Coulomb's law, and boom, you completely bypass the calculus trap. Oh, and here is another incredibly specific, recurring numerical trap you absolutely need to memorize. When you're looking at the electric field of a uniformly charged ring along its axis, the field is 0 at the center and 0 at infinity, right? That means there must be a maximum somewhere in between. By differentiating the formula, we find that the exact distance where the electric field hits its absolute maximum intensity is exactly r divided by the square root of 2. Burn this number into your memory right now because it shows up constantly in JEE Advanced numericals. Moving right along to section 2, flux, potential, and symmetry. Gauss's law is easily one of the most powerful tools in your entire toolkit, but its successful application completely depends on selecting the right surface. Mapping the distribution symmetry to the correct Gaussian surface is literally half the battle won. Got a point charge or spherical distribution? Just use a concentric sphere. Dealing with an infinite line charge? Wrap that in a coaxial cylinder. Working with an infinite plane sheet? A cylindrical or cuboid pillbox is your go-to. Match the symmetry correctly and the math just simplifies beautifully. But be warned, standard cases use uniform charge densities, sure, but JEE Advanced, they love to throw you straight into the non-uniform density trap. In these scenarios, the volume charge density, rho, actually varies with radial distance. You can't just simply multiply density by volume anymore. No way. You're forced to integrate the variable density over the specific volume element to find the true enclosed charge. This is specifically designed to test your proficiency in translating physical laws directly into calculus, which is a fundamental requirement if you want to crush the advanced exam. All right, into the heavy-hitting stuff. Section 3, conductors and capacitors. When inserting a dielectric slab into a capacitor, you absolutely, unequivocally must memorize how capacitance, charge, voltage, and energy shift in two very specific scenarios. So the crucial point is knowing the difference between when the battery is kept connected, meaning voltage remains constant, versus when the battery is disconnected, meaning the charge remains constant. For example, if isolated, doubling the plate separation halves the capacitance, which actually doubles the stored energy because of the external work done. Knowing these shifts without hesitating is non-negotiable. Let's move to and see how this builds into an amazing shortcut for one of the toughest problem archetypes you'll face: concentric metallic shells. Specifically, we're talking about those tricky earthing problems where you need to find the charge flown to the ground. Instead of setting up complex, multivariable potential equations and setting them all to zero, you can just use this three-step topper hack. Sum up the internal charges, then simply add a fraction of the external charges, which you calculate by taking the earthed radius divided by the external radius. It's an incredibly elegant shortcut that literally saves massive amounts of time on the clock.
Which brings us to the brutal hallmark of the exam, Section 4, the mechanics fusion trap. And this brilliantly illustrates exactly what I mean. Take a good look at these real geometry setups pulled straight from past advanced papers. You aren't just given two simple charges on a straight line. No, you're analyzing electric dipoles shifting coordinates in an XY plane, or maybe a central charge interacting with multiple charges arranged around a regular hexagon. The exam makers are actively testing your geometric distribution knowledge, your vector calculus, and your real-time 3D spatial reasoning, all at the exact same time. A classic archetype of this domain fusion is electrostatics simple harmonic motion, or SHM. They love giving you a system in stable equilibrium, say a charge perfectly balanced between two other charges, or maybe a dipole perfectly aligned in a uniform field. Then they ask what happens if it's slightly displaced. You have to instantly recognize that this creates a restoring force, resulting in SHM. You must be ready to quickly calculate the time period, either using the standard linear formula or the angular oscillation formula utilizing moment of inertia and dipole moment.
And finally, the home stretch, Section 5, winning the JEE endgame.
If you want to avoid the examiner's traps, this is your rapid-fire must-master checklist, pulled directly from the last 15 years of paper analysis. Ready? Number 1, master calculating concentric shell potentials and grounding shortcuts. Number 2, know the battery on versus off dielectric shifts by heart. Number 3, be able to visually identify electric field and potential versus distance graphs for both hollow and solid spheres. Number 4, practice integrating Gauss's law with non-uniform variable charge densities. And finally, number 5, be ready to calculate the torque and time period for dipole angular simple harmonic motion.
We've unlocked the core formulas, we've revealed the topper shortcuts, and we've completely decoded the multidisciplinary traps hidden within the JEE Advanced papers. Electrostatics really doesn't have to be the monster chapter anymore. It can absolutely be the chapter where you pull ahead of the pack. So, looking at everything we've just broken down, are you ready to beat the examiner at their own game? Grab your notes, hit those practice problems hard, and I'll see you in the next explainer.